Welcome everyone, and good morning, good afternoon and good evening, depending on where you are in the world currently. My name is Peter Negline and I'm based in Singapore with BOC Aviation. I'm also a director of iStat, and it's a great pleasure to have you all with us today for our iStats Learning Lab, where we're going to hear and learn about sustainable air travel. We're delighted to have with us today Glenn Llewellyn, who is Vice President of the Zero Emission Aircraft project at Airbus, an international pioneer in the aerospace sector and well known, I'm sure, to everybody involved with iStat. Glenn is widely recognised as a top-tier leader on climate strategy for aviation. Today, Glenn is at the helm of a zero-emission revolution at Airbus with the mission to unite all the ingredients needed to launch the world's first zero-emission commercial aircraft program, known as Zero E. Prior to his current role, Glenn led the research and technology portfolio dedicated to reducing the climate impact of Airbus's products. This portfolio included all-electric vertical takeoff and landing aircraft, including Vahana and City Airbus, as well as the hybrid electric E-Fan X. Now, before Glenn starts his presentation, I'd like to mention to those listening live that you can ask questions via the Q&A icon, which is at the bottom in the middle of your screen. And I want to strongly encourage all of you to not delay or be shy in asking questions, because today we've promised Glenn that we will wrap up this session at the top of the hour. So we have less than 60 minutes in total. So with that, Glenn, many thanks for your time today. Look forward to hearing your presentation. The floor is all yours.
Great. Thank you, Peter. And really glad to be with you all today to share with you an insight on the Zero E, the Zero Emission Aircraft project that we have started at Airbus. I will just share my screen. And what you should see in a few seconds on your screen is an image of the 3 aircraft which we revealed in September last year, which are 3 concept aircraft in our family of zero emission aircraft that we are studying. You can see 2 what we call tube and wing configuration aircraft, so a turbofan in the front of your image, a turboprop towards the rear of your image, and then a blended wing body towards the left. All of these aircraft are hydrogen powered aircraft, and we believe that hydrogen really has the most potential compared to every other option to reduce or potentially eliminate aviation's climate impact. And I'd like to share with you a little bit about why we're doing this. This is a massive shift for our industry. It's something which we've reflected a lot on, and I'd like to help you understand why Airbus is going in this direction. I'll share with you a little bit more detail about the aircraft and then about some of the technologies that we are working on and progressing as part of the project. So first, a little bit about the why. Many of you will have seen the change in societal expectation and also in terms of regulatory expectation when it comes to climate. We've seen that very much so from Airbus. We started this zero emission project soon after the Paris Agreement, trying to understand how we need to change our business for the future. In 2019 and 2020, and even the beginning of 2021, we've seen the trend accelerate quite significantly. The UK, the first major economy to pass a 2050 net zero emissions law in 2019. The EU Green Deal first announced also in that year, at least in terms of intention. New Zealand putting something in place towards the back end of 2020, very similar to what the UK had implemented. The EU Green Deal getting enacted into law in 2020. China stating its ambitions in terms of climate neutrality. Japan, South Korea in the end of 2020, and then of course the United States rejoining the Paris Agreement, the Leaders Climate Summit, creating, I think now, a really global movement, a global coalition of countries who want to meet the Paris Agreement or even beat the Paris Agreement. And that is going to change the ecosystem in which we are all operating in which our businesses are operating in. And we want to position Airbus and the aviation industry to be able to provide the positive service that it provides to society through connecting people without the climate impact. There is no problem with aviation. Aviation is a social good, but there is a problem with CO2 emissions. And what we want to do through this project is to address that. The aviation industry has set itself extremely ambitious targets in terms of overall emissions reduction. And what we see when we analyze the changes that need to be made, the changes in terms of aircraft performance improvement, the changes in terms of energy carriers, what we see is that all of those are needed. There's really no silver bullet. It's going to be a combination of multiple pathways which gets us the result that we need. We see sustainable aviation fuels as being significant. Biomass-based fuel is certainly one significant part of the pathway to get us eventually to zero. At the same time, what we want to encourage is the development of what we call synthetic fuel pathways. We believe that the synthetic fuel pathways will provide the scalability, will also over time provide the economics, which allows aviation to continue to grow and to emit significantly lower emissions over the coming decades. If we look at this sort of energy roadmap over time, what we can recognize today is that biomass-based fuels are already available. There's basically no technology blocker in the way of biomass-based fuels being deployed. They are already used on our existing aircraft. Our aircraft are in fact certified to carry up to 50% of sustainable aviation fuel on board. What is missing are the incentives and regulatory frameworks which encourage airlines to have more uptake of sustainable aviation fuel. And certainly we believe that it's mandatory to get increased uptake as we progress through the 2020s. In addition to this biomass-based fuel pathway, what we absolutely need is pathways which are a result of renewable energy, or which are created by renewable energy processes. So this means that we need it to be recognized that aviation can be powered by renewable energy. Of course, we can't put solar panels and wind turbines on board the aircraft, but by leaving them on the ground, we can create surrogates for that renewable energy, which we can then take on board the aircraft, thereby powering aviation with renewable energy. Direct air carbon capture is going to be a key technology in allowing us to do that. In the first phase, direct air carbon capture, we believe, can be used as a means of sequestering CO2. And in a latter phase, the direct air carbon capture would be used to capture CO2 out of the air, which would then be an ingredient in the power to liquid synthetic fuel. And power to liquid synthetic fuel also requires hydrogen as its other ingredient. It's a hydrocarbon, so it needs hydrogen and carbon to create this synthetic fuel. On top of that usage for hydrogen, what we're pushing extremely hard with the ZERO-E project is the possibility to use hydrogen in its raw form on aircraft, on large commercial aircraft. We think hydrogen has huge potential compared to all of the other options, both in terms of climate credentials and in terms of cost. And what we very well understand is that if we can make the economics right, the solution will grow faster than any other solution, and therefore it will have the largest possible benefit in terms of climate. So the economics of the aircraft and the energy that powers the aircraft is key in bringing the right solutions to market. Once we start to say that we want to power aviation with renewable energy, it's really important to understand the renewable energy ecosystem. And what we've seen over the last decade or so is actually very impressive growth. For sure, in terms of absolute numbers, the growth level is not where we would like it to be to for example, be already meeting the Paris Agreement. But in terms of trend, there is really something promising behind the data. If you consider that the period that you're looking at on these charts now is the period most of the time prior to the Paris Agreement, it was also prior to the coronavirus, which means prior to all of the initiatives to grow back green after COVID, which are having a huge impact on the amount of investment in renewables and in green tech. So during that period, we already had doubling, we've had multiplied by 5 the total installed photovoltaic and wind generation across the globe. And our view is that this trend is going to accelerate and that we're going to see these numbers getting much larger over the coming decades. And it's one of the reasons why we want to position aviation to be powered by renewable energy, because with this massive scale up, we believe that cost is going to come down. Because cost has already been coming down and shows signs of being able to come down even more over time. The improving technologies, the improved efficiency of some of the technologies, the competitive supply chains, the scale up in terms of industrialization of these different technologies has already allowed quite significant cost reduction over time. And all of the analysis is telling us, but also telling independent players, that there is still quite significant potential to bring down the cost of renewable energy. And if we now zoom out, what you see on this chart is the 2010 to 2020 period. That's the period that we've just been talking about in terms of quite fast growth, in terms of quite fast cost reduction. What you see is that that's peanuts in terms of the total growth in renewables, which is going to be required to get us to where we need to be by 2050. Those growth curves are really only a small start at the growth that we're going to see. And therefore, the cost reductions are going to be potentially much more significant as this technology is scaled into the next decades. What's also really important for us is the hydrogen economy. So we're interested in particular in the green hydrogen economy powered by renewables and electrolysis. We know that if aviation was the only industry on the demand side, that we probably wouldn't be able to accelerate the ecosystem to the level we need. But what we see is multiple industries. Here are some examples in the transport sector, but there are others in steel manufacturing, in cement manufacturing, even in home heating, that are looking very, very seriously at hydrogen as the most economic option for decarbonization. And what we see is massive progress over the last 2 years in terms of the announcement of concepts or even the commercialization, the already commercialization of these technologies. When we first started studying this at Airbus post Paris Agreement, we could see from our analysis that hydrogen was going to be a big part of society's way to meet the Paris Agreement, but we saw very little signs of hydrogen in terms of demand and in terms of supply in the wider ecosystem. We didn't see much news, we didn't see much development in the different companies we were speaking to at that time. When we now look out our window at the various different industries, there's a huge change. There are now 8 truck companies who are either developing hydrogen concepts or even have hydrogen trucks either under test or commercial application today. We have the train industry, which is not just looking seriously, but has already deployed hydrogen fuel cell trains to replace diesel trains, where it's cheaper to put a diesel train or several diesel trains on a route than it is to add the electrical cables overhead, which can also be, let's say, not appreciated by the local community. So there are several advantages there in terms of hydrogen for that sector. We see shipping, not necessarily long haul deep sea shipping, but shorter distances, ferries, for example, intracontinental shipping, moving towards hydrogen as one of its preferred options for the decarbonization of its sector. The ship in this image here was in fact launched in November last year, and it's just going through the fitting of the propulsion system as we speak. There are literally hundreds of fuel cell buses on the road today across various geographies. And so we're starting to see several industries pulling the hydrogen ecosystem. And what's on top interesting for us at Airbus is that there are some players, particularly intracontinental shipping and trucking, that are also pulling in the direction of liquid hydrogen as the preferred storage solution. And that's important for them for the same reason that it's important to us, which is better payload and better range capability with liquid hydrogen compared to compressed gas hydrogen. And so there are synergies being developed across multiple sectors, both in terms of the development of the hydrogen, liquid hydrogen infrastructure and ecosystem, but also in terms of liquid hydrogen technologies, which are going to be important for all of us. If we then look specifically at aviation and where hydrogen is going to help us in terms of reducing and maybe even eliminating our climate impact. There are three basic options for how we use hydrogen on board our aircraft. I'll speak first about power-to-liquid synthetic fuel. I mentioned it earlier when we discussed the energy roadmap. Power-to-liquid synthetic fuel, it's the fuel where you have direct air carbon capture, taking CO2 out of the air, providing the carbon for the hydrocarbon, and hydrogen providing the hydro. The advantage of that fuel type is that it is already compatible with existing aircraft, up to 50% on aircraft already certified today, and we will quite easily certify up to 100% over the next few years. So technically, it's not going to be a huge challenge. And then what we're going to talk about really for the most part of the remainder of the presentation is really the bottom two boxes, where you have two basic options. You also have a combination of the two as one of your options. And this is where you have raw hydrogen on board the aircraft. You, in the hydrogen combustion option, you are combusting that hydrogen in a gas turbine that's fairly similar to what we have on our aircraft today, but obviously needs to be modified to cope with the combustion of hydrogen, the fuel system, which needs to provide hydrogen instead of kerosene. So there are, nonetheless, even if the basic technology is the same, there are some modifications. The other option is hydrogen fuel cells, and there are various players in the general aviation space looking at hydrogen fuel cells for powering aircraft. Hydrogen fuel cells take hydrogen and oxygen, and using both of those products create a chemical reaction which has as a byproduct electricity and water. And fuel cells can be used to power electric motors, and then electric motors can be attached to, for example, propellers. So we're still working on what the scalability and economics is of such a kind of propulsion system. And then we can potentially combine the two by creating a hybrid electric propulsion system. Instead of using batteries on board the aircraft, you're using fuel cells to provide the electrical power when the fuel cell performance is operating at a higher level than what the gas turbine is at certain phases of flight. And therefore, ZEROe, really what it's focused on, and the reason we've chosen hydrogen and these kind of propulsion options as the solution we're looking at, is the lowest possible climate impact for this world that we know is going to be in the future, and the lowest possible cost per ton of CO2 avoided, which we think is what will have the largest climate impact because economically it will scale. The three aircraft which we looked at the very beginning are detailed a little bit more here. So we have the turbofan at the bottom, blended wing body in the middle, and the turboprop at the top. The blended wing body is probably the one that the media have certainly been the most excited about. It's for sure an attractive long-term option, but it is the least likely of the three options in terms of what we're going to take to market by 2035. It has a completely new airframe and set of aerodynamics, combined with a very different propulsion system. We judge it to be too much to change both in one single step. So the more likely configuration that we'll take to market is the one of the options between turboprop and turbofan, because even if there are some changes at the overall aircraft level, for example, in these images, the eagle-eyed among you will spot that the tail is slightly longer than a classical kerosene aircraft, and that's because the hydrogen is stored behind the rear pressure bulkhead in the rear of the aircraft, and that for sure has an impact on overall aircraft design, but it's relatively minimal compared to the blended wing body, and then we can focus our energy on the propulsion system, which is where the real changes are and where the most significant change is in terms of reducing aviation's climate impact. The other really interesting numbers which come from the studies we've done are that hydrogen has quite a huge versatility. So hydrogen can be used to power aircraft all the way from general aviation aircraft up through 100-seat, 200-seat aircraft, 1,000 nautical miles, 2,000 nautical miles, and we can even see us going beyond those sort of numbers in the future. That's a large part of the aviation market. It's a large part of aviation CO2 emissions and climate impact, and therefore huge potential for hydrogen to play a significant role in reducing aviation's climate impact. All of these aircraft are the aircraft that we revealed in September 2020. They are all hybrid electric aircraft, so meaning that they have a gas turbine and a fuel cell on board in a hybrid electric configuration. This aircraft is a concept we revealed in December 2020. We didn't reveal it in September because there was still some intellectual property that needed to be secured. And this aircraft is quite different from the three on the previous slide, in that this aircraft is an aircraft that's fully powered by fuel cells. It has, in this case, 6 propulsion units. Each of these propulsion units or pods have the electric motor, power electronics, fuel cells, and in fact also have the hydrogen storage located in these pods beside the rest of the system. It's a concept that we're still studying. It's a concept that we're exploring in terms of its scalability and its economics. It's interesting in terms of its climate impact. There is no combustion and therefore no NOx. Contrails could probably be close to zero because you can manage how the water leaves the aircraft, but still lots of better understanding that we need to have in order to really understand the sort of scale that this kind of technology could go to. I've chosen this image just to give some examples of the technologies that we're working on in a bit more detail. The hybrid electric has all of the technologies that we're interested in it. The fuel cells, for example, are still in a hybrid electric configuration, even though they are more dominant. There is much more power installed if the aircraft was to be fully powered by fuel cells. And what we see are certainly some major technologies that we need to develop. We need to improve the performance of, we want to reduce the weight of, in order for it to be relevant for commercial aviation applications. The hydrogen-powered gas turbine is something in terms of technical feasibility, which is already being demonstrated. In the 1950s, B-57 flew with the US Air Force, powered by hydrogen. In the 1980s, a Tupolev 155 flew with hydrogen. So in terms of basic fundamental technical feasibility, that's demonstrated. Now what we need to do is develop that technology further in order to make it adapted to commercial aviation. And we have engagements with all of the major engine manufacturers as part of our work to do that. The liquid hydrogen storage is another key technology for the aircraft. In this case, we're talking about technology from the automotive industry. It's a technology which was actually deployed commercially in a hydrogen car in the 2010s. It's a twin-walled vacuum insulated tank, and it keeps the hydrogen at cryogenic temperatures. So again, the technical feasibility of the technology at the most basic level has already been demonstrated, but we have work to do to scale it, to bring the weight down, to introduce the necessary systems around it for commercial aviation applications. Fuel cells, also a key technology. We have announced in Q4 2020 the creation of a joint venture with a player in the automotive industry, where we have taken what we judged as the best performance automotive fuel cell stack and are now in the process of developing it further in terms of efficiency, in terms of kilowatts per kilogram, so power to weight ratio, and in terms of operating temperature, in order to really take it to the next level and get it ready for commercial aviation applications. In order to convert the electrical energy, which is going to be developed by the fuel cells, into shaft horsepower for the propellers or for the fans, we need power electronics and electric motors. So another key brick in the overall technology that we need to develop. Excuse me. So now a little bit about hydrogen and comparing it to kerosene, which I'm sure many of you will be familiar with. For the same amount of energy, hydrogen is 3 times lighter. So it weighs less than kerosene in terms of kilograms. The challenge really with hydrogen comes when you look at the volume. And here there are different ways of storing hydrogen and therefore different volumes. If you store it in gaseous form at 1 bar of pressure, you end up with 1 liter of kerosene being equivalent to 3,000 liters of hydrogen. So that's clearly not going to be acceptable for a commercial aviation application. When you start to pressurize it, you can improve things. You can take that 3,000 to 6 liters if you pressurize it at 700 bar. That's about the limit of what the automotive industry is doing, so that gets you to that point. And then what we want to do for the aviation applications is liquefy it. So turn it into a liquid, which means cooling it cryogenically. And once we do that, we can get it to 4 times the volume of kerosene. Still a difference. There is still a difference in volume compared to kerosene, but with the weight difference being helping us in the positive sense, the penalty in terms of volume is somewhat counterbalanced at overall aircraft level. The hydrogen, once we decide to store it cryogenically, gets stored in a twin-walled vacuum insulated tank. That is super insulated, with an outer jacket, an insulation layer, and then an inner vessel. And as I mentioned earlier, that technology has already been demonstrated in the automotive industry, but it's something we are working on in order to develop it for aviation, commercial aviation applications. Then there's a question about where do we store hydrogen, given that it has extra volume compared to kerosene, and the way we store it is quite different in these twin-walled vacuum insulated tanks. It leaves us with various options for storing the liquid hydrogen on board. And the concepts I showed you earlier and the concepts that we've revealed to the public are a subset, a small subset of the concepts, the total amount of concepts which we've been studying. We can't store liquid hydrogen in the wings. So we've got to move towards podded configurations, dorsal configurations, caudal type configurations. There are configurations which are sort of hybrids between some of the configurations on your screen and others that I'm not going to go into detail on. But clearly the design space is opening right up in terms of aircraft configuration. And we're in the process right now of converging on what will be the final aircraft concept that we want to take to market by 2035. And the tank configuration is obviously going to be a big part of that. Then in terms of the propulsion system, we spoke about hydrogen combustion having similar principles as the kerosene gas turbine, but with several components which are changed. The combustion chamber, the injectors, we need cryo heat exchangers to take the hydrogen from cryogenic form to liquid form up to gas form. And we need hydrogen pumps. Today's kerosene pumps are far different from what we have as requirement for hydrogen aircraft. The feasibility in terms of basic feasibility has been demonstrated since the 1950s. The other way of generating power on board the aircraft is with fuel cells. So we produce electricity to power electric motors. Water is the only byproduct, and we have higher efficiency in the fuel cells, but higher weight and drag versus a gas turbine. So important to be able to analyze all of this at aircraft level and decide for the different market segments what the best option is for the economics of the aircraft. We also can combine the two kinds of propulsion systems that I've been talking about. We have the gas turbine, which can also be powered by an electric motor. So you have an electric motor embedded on the central shaft of the gas turbine. That is then powered by fuel cells and all of it powered by liquid hydrogen storage. The reason we would do that is because you can have several hybridization strategies which overall make your propulsion system quite efficient. You can boost during takeoff and climb using the electrical power source, which reduces the sizing of the gas turbine and makes it more economical during cruise. We can have assistance in the transient phases as it goes from one phase to another, coming from the electrical sources, and we can have a reduced consumption descent where we idle back the kerosene, or sorry, the combustion part, and we use the fuel cells to power the engine. All of this enables us to increase the gas turbine efficiency and the overall propulsion system. All of that technology is a key part of the Zero E development, and it's mandatory that we're successful in advancing the technologies over the next few years to the point we need. On top of the technologies, it's going to be critically important to have the right ecosystem. You will all know that hydrogen doesn't exist at most airports. Where it does, it's only in small quantities. And if we want the Zero E to be successful, that has to change. So we're working with several players. There will be many announcements over the next years about collaborations which we have initiated on this topic because it's critically important for the overall success. We believe that during the 2020s, airports can become hydrogen hubs, serving the wider community, serving the local airport ecosystem with zero-emission hydrogen. Airports are heavy vehicle hubs. Trucks go to airports because they are cargo hubs. Buses go to airports because they're passenger hubs, and aircraft, hydrogen aircraft, will go to airports because they are passenger hubs. So all of this makes airports ideal candidates to be hydrogen hubs, where they can serve numerous applications already in the 2020s, preparing for the scale up of hydrogen for aircraft in the 2030s. Our overall timeline starts really with 2035. This is the entry into service date, which we are targeting for the first zero-emission aircraft. And if we work back from that, what it essentially means is that we need to have decided on the product we want to take to market by around 2025. And between now and 2025, we need to decide the aircraft configuration, including some of the questions we shared earlier. We need to mature the technology. We need to flight demonstrate propulsion systems, so hydrogen propulsion systems. We need to demonstrate them in flight before we finalize the product selection. And then we also need to establish the ecosystem, which, as I mentioned, is critically important to the overall success. We had the pre-program launch in September last year, and the project start for Zero E specifically in 2018. I believe that this is a very exciting adventure for Airbus. I think it's hugely important for the aviation industry. If you think you can help bring zero-emission aircraft to reality, please reach out. We recognize that this is a team sport and one that we will need to join together in order to achieve. And I'm looking forward to your questions.
Excellent. Thank you very much, Glenn. I really appreciate that. It's very, very insightful. We do have some questions online. And before we start with those, can I just remind all of the audience that you can ask questions through the Q&A tab in the bottom of the middle of your screen. So we'll get straight into it. The first question, which is probably not so easily answered right now, Glenn, is that Patrick asks about percentages on some of the slides regarding different emission reduction measures at the beginning of your presentation. Would it be possible to, first of all, to get a copy of the presentation, and then secondly, to have some of those numbers put on those slides?
Sure. So I can definitely share the slides, maybe to give a rough answer right now. So we estimate that hydrogen in its various forms, so this means synthetic fuel as an ingredient to synthetic fuel, and also as used in its raw form on aircraft, it's going to contribute, it needs to contribute around 50% to 50% of the CO2 emission reduction that the aviation industry needs to achieve. So hydrogen is going to be massive, needs to be massive if we're going to achieve our targets.
Okay, thank you. The next question comes from Paul, who asks, when talking about H2 or hydrogen for aircraft in the Zero E series, would that be fuel cell powered electric aircraft? So I think you may have answered this, or how does aircraft consume the H2, the hydrogen fuel?
Yeah, so we're still studying all the various options we've got in terms of propulsion system. We don't need to make that decision yet, and so we still have more aircraft design work, more maturation work, and more test work before we'll finalize what propulsion system we take forward for the Zero E aircraft.
Can I just ask though, on that, with regard to, you sort of mentioned there's so many different areas where you are focused in new technologies and other developments, but do you have, or do you think you have right now, the sufficient network of partners that are cooperating or active in those areas to work with you, or are you still searching for other partners in particular areas?
So we've already got a good set of partners that we've started working with. I mentioned we've set up the joint venture on the fuel cell stack technology. We've got various partners that we're working with on liquid hydrogen storage and distribution. We've engaged the engine manufacturers in terms of developing hydrogen-powered engines. So I think we've got already a very good let's say, wider team or extended team that's going to help us develop this. What I'd say is that as we are all moving towards carbon neutrality, these technologies are going to evolve very quickly. So if somebody thinks that they've got a technology which could be of interest for an aviation application, perhaps lower weight, perhaps lower cost, perhaps simpler in terms of design, in terms of liquid hydrogen storage, distribution, fuel cells, electrical technologies, hydrogen combustion, you know, we would welcome exchanges with those players, recognizing that we need to remain humble in such a dynamic space.
I understand. Excellent. Thank you. I have two questions here from Sundar. He begins by thanking you for the excellent presentation, but he goes on to ask, a lot of your new innovations, sustainable aviation fuel, hydrogen-powered aircraft and the like, seems like it requires a combination of engine OEMs, and how are you working with them to achieve these objectives?
Yeah, so we're currently engaging with engine manufacturers. The reality of this is that it's definitely a team sport. It includes aircraft manufacturers, it includes engine manufacturers, and it includes energy suppliers, airports, and even regulatory bodies, right? So we have done something that we never usually do by communicating in 2020 about our intention. Normally in the aircraft industry, we hide for as long as possible our plans in terms of aircraft development and reveal it more or less when everything's been decided and finalized. We recognize that this is way different in terms of challenge, and the only way we were going to build the team, and really this is a wide team, as I said, including regulators, including airports, including energy suppliers, including engine manufacturers, various technology providers. This had to be communicated, and it was because of that we had a big event in September 2020 to share with the world why we're doing this, what we're doing, and to call for action to help us go in this direction.
Well, can I ask then, in making those decisions, and as you say, leading up to the presentation in September 2020, why do you think other people in the industry are perhaps not looking at this in such an ambitious manner and relying on things like sustainable aviation fuels to achieve their objectives rather than something more ambitious?
Yeah, so I think sustainable aviation fuel is an important part of the jigsaw. It helps us with the current aircraft, for example, which hydrogen doesn't. Where hydrogen is really interesting is when we look at the overall climate impact and when we look at the economics. And I think we have maybe a very specific view of the problem statement. We believe that all of aviation's climate impact in terms of NOx, in terms of contrails, has to be considered when we look at the medium and long-term plan for our products. And sustainable aviation fuel doesn't solve the complete problem. So we're focused on all greenhouse gases, all climate impact. And that's what drives us to hydrogen and drives us also to some urgency around hydrogen, because I think, you know, we all saw it during 2019, 2020, how societal expectation, how our individual expectation has perhaps shifted with respect to this subject. We have a certain amount of urgency as a business priority, as a moral priority, to bring solutions to the market ASAP.
Excellent, thank you. Look, we'll get back to the questions from the audience. Sunder's second question was, based on the recent STEER report, which I must admit I'm not familiar with, but the STEER report, it seems that the greatest reduction in CO2 emissions are directed at wide-body aircraft. With the pandemic reducing the demand for these aircraft, is Airbus thinking about reduction in wide-body production as a natural hedge to reduce CO2 emissions?
So I'm not really going to answer questions about production and ramp up and so on. I think if we just zoom out and look at the origin of the question, which is about proportion of sort of short, medium range to long range emissions, what we see is that it's about 50-50. So for sure, hydrogen is not solving the full challenge, but 50% of this challenge is already significant. And that's a massive market, a massive business, and a massive opportunity if we can bring zero emission aircraft products to market for that space.
Okay, thank you. The next question is from Hariam. I hope I pronounced that correctly. Hybrid aircraft are very interesting from an ecological point of view, but isn't it shifting the problem of pollution? The plane may not pollute anymore, but the production of those new energy sources are polluting. Your thoughts?
So that's really a valid point. We have to, and it's again one of the reasons why we communicated in September 2020, we have to have green hydrogen on our aircraft. That's what we are pushing to have at airports. That's what we're working with energy suppliers and airports on. There is absolutely no interest whatsoever. In fact, it would be worse if we were to use grey hydrogen, so hydrogen from fossil fuel, to power the aircraft. So it's absolutely crystal clear that we are interested in zero carbon hydrogen for these aircraft. It's not just the aircraft emissions itself. We have to consider the life cycle of that energy source in our calculations. It's super important.
Okay. Hariam's second question is, why can hydrogen not be stored in the wings of an aircraft?
Because you essentially take up too much space with the twin-walled vacuum insulated liner, which reduces your volume to almost negligible inside the tank.
Okay. An anonymous question.
Inside the wing.
I understand. One of our audience has asked, how does Airbus envision the necessary change in infrastructure to supply hydrogen around the world by 2035? I think you've touched on that a little bit already.
Yeah. So we've discovered, I guess, a number of things since we first started this project about the ecosystem. You can certainly imagine that at the beginning, when we first started on this, we thought, okay, look at the thousands of airports around the world, and how do we get those equipped with hydrogen? And especially during the transition, as you move from kerosene to hydrogen, how are we going to manage that? Because that's almost mission impossible. And then you sort of step back from that and you think, well, how is this realistically going to happen? And ultimately, what we will start with is strategic hydrogen hubs. And what we've been surprised about is that how few strategically located hubs we actually need to equip with hydrogen infrastructure to have literally hundreds of aircraft operating. One of the key design drivers for us is to be able to do an interesting range in order to go out and back without needing refueling at the outstation, which for the very beginning of the transition is going to be really important, because it means that you can do masses of hub and spoke activity without much hydrogen infrastructure. And because hydrogen weighs so little, and because you're not emitting CO2, neither in the life cycle sense nor in the emission sense, it's not costing you much, neither in terms of economics nor in terms of environmental impact, by doing this tankering that you would do during this initial phase. And so once you start breaking down the challenge, you start to see that actually it's much more reasonable than what we initially thought. And then what's even interesting is to look at other sectors. For example, trucking industry. We have many advantages compared to the trucking industry because aircraft always go from airports to airports. Trucks take much more random routes around countries than aircraft do. And so, in fact, developing hydrogen infrastructure or even electrical charging infrastructure for ground vehicles using roads is actually way more complicated than it is to think about how we're going to equip aviation with hydrogen. I don't want to sort of underplay the challenge. For sure, it's a big change. For sure, there's going to be lots of work to do, but I think it's going to be easily achievable and pretty reasonable in terms of transition.
Okay, interesting. Thank you. The next question is from Bernd, who has a two-part question. You've answered the first part, but he asks, can you talk about the impact of burning hydrogen on aircraft engine maintenance?
Yeah, so we're working with engine manufacturers. Our target and their target is definitely to achieve equivalent sort of maintenance levels as what we achieve with existing aircraft. We still have some work to do to get there, but that seems to be something that everybody believes is achievable.
Okay, thank you. The next question is, do you see carbon taxes helping economic incentives overall?
I think if you look at the mechanism of carbon taxes, you certainly penalize, but you don't incentivize. And I think what we're going to need is to be making sure that we inject money into the solutions that we need, whether the solutions are renewables, whether the solutions are technology-based. We've got to make sure that money gets invested into the ecosystem and the technologies that we all need. So aviation, but all the other industries as well, to achieve the Paris Agreement. And I would just maybe add to that. I think one of the clever things which we're shaping in different regions of the world at the moment is what we're doing is we're taking technology from the ground sector, from automotive, we're taking technology from the space sector, we're taking technology from the energy sector, and we're improving the performance of it for commercial aviation applications. If we're clever about how we do this, what we can achieve is to feed that technology back into the energy sector and the ground sector in particular, so that they end up with the performance improvements which have been paid for by preparing for zero emission aviation. And so there can be a sort of greater societal benefit in developing the technology, which helps ultimately with the wider transition of society to zero emission solutions.
Excellent, thank you. Glenn, we're at the top of the hour, but if you can bear with me just a few more questions. This one from Mark, who thanks you for your presentation, but he asks, how does Airbus square the circle between A, the hard sell and production of many CO2 emitting aircraft as possible in the present business, and B, the production of zero aircraft at scale in the 2040s?
So the current aircraft are capable of flying with sustainable aviation fuel. What we need to do, and we advocate publicly for it, is increase the amount of sustainable aviation fuel on board the aircraft, incentivize the ecosystem such that the costs come down, such that there is much more availability of that fuel type. And then those aircraft can fly with significantly lower emissions. And yeah, then in the 2030s, in the 2040s, we're going to see massive ramp up of zero emission aircraft. Our view is that there's potential that these products become the best selling products and actually the future products of Airbus. And for sure, there's an industrial challenge there, but I think we've previously demonstrated our ability to meet pretty impressive industrial challenges, and we'll put that experience to good use when it comes to bringing zero emission aircraft to market.
Thank you. The next question is acknowledges the exciting technologies that you've described today, but it goes on to ask, how big is the team at Airbus working on the technology, and how big do you think the team grows to in time?
So we're several hundreds right now, and we will grow to thousands as we go towards a fully fledged program development. So really significant numbers of people. And you know, you can see some interesting dynamics here, because essentially we're developing people in green tech. These are people who have been working on, let's say, the existing product range, and now are green tech experts. And we've for sure got to develop that further. I think competencies is going to be a challenge for society overall in green tech. But I think it's very exciting, very motivating for people to be involved in the development of green tech to allow us to meet the Paris Agreement.
Okay, thank you. I'll skip over a couple of questions because we've broadly answered them earlier, but I'll conclude with the final question here from Paul, who asks, how much of existing engine hardware could be used in hydrogen aircraft? I gather Paul might be an appraiser, but he's asking from an appraiser's point of view, could a kerosene based engine be reconditioned to consume hydrogen, or is there any scrap value in a kerosene engine in a hydrogen world?
To be honest, it's probably a question better asked to the engine manufacturer. I think from a basic technology perspective, there's certainly a lot of reuse that you can do. In fact, you know, the engines which have flown in the past have been repurposed. The engines that have flown with hydrogen in the past have in fact been repurposed kerosene-powered engines. Now, what would you have to do if you wanted to sort of put it back into commercial service? Yeah, I think that's a question for engine manufacturers.
Okay, I appreciate that. Well, look, on that note, we're going to wrap up there. Glenn, thanks for staying with us beyond the hours, taking a little bit more of your time. It's been really, really insightful and very helpful to open my mind, at least, in terms of how big this issue is and how much more thinking there is to do as we go forward. So I wish you and your team every success. And I thank our audience for joining us today. It's been fantastic to learn about this topic and to have you all involved with us, and want to encourage everybody to stay in touch with ISTAT and our online activities. And you can find everything related to that at istat.org under the online tags there on the front page. So thank you again, Glenn, and thank you everybody for joining us today.
Okay. Thank you, Peter. Thank you,
you.
everyone.
Bye-bye.